Okay, this is Calc 4, lecture 32, or Calc 2, lecture 22. That is Euler's method. So this is the first baby step in what we call numerical analysis or numerical mathematics. Maybe the integration, the approximate integration was maybe the first baby step. But anyway, so what we do in numerical mathematics is undo limit, in a sense. Calc starts with limit. This one is going backwards, so we have to get rid of the limits, because limit means something goes to infinity, and infinity doesn't mean anything for the computer. So, how do we undo the limit? I will stick with this one, which is dy dx. So that's how we do it. Instead of writing dy dx, we say, okay, this is approximately delta y over delta x. And I mentioned at some point that this dy dx can be treated as a fraction. And I also mentioned that's because this is almost this, and this is in fact a fraction. And instead of using this, we use this. So first we write it like this, the dy dx, and we say, okay, if this is equal to this, or approximately, then this should be approximately the right-hand side. So this is f of x, y. And then we cross multiply, and this gives me, let's get rid of this approximate. Delta y equals f x y delta x. Okay. Then if I start at x0 with the value y0, I have to choose some delta x. So 1, choose delta x. You see, delta x in this situation goes to 0, right? So delta x technically approaches 0. But here, what does that mean for the computer approaching 0? So we have to choose some delta x. And let me also say what the problem is asking us. So it's saying that find, say, y at certain times, say y at, say, 10. So it's asking for the value of the function at 10, whatever that is, x or t or time, for example. So it starts at 1 and ends at 10, and it's asking for the value of the function at 10, given that the function satisfies this differential equation and it starts here. So choose delta x, then use the initial condition, and delta y equals fxy delta x to find, say, y at certain x for a given x, say given x. Okay, so that's all you do. You start, and I will give you an example. I can just go for that one, the one that I gave as an example, and try to find y at 10. Well, I cannot do it here on this board. I need some calculator or something to do that. But anyway, maybe I just go for, say, y at 3, say. Anyway, so let me show you what this means geometrically and what you are doing. So Remember from Calc 1 that a function, say, it can be approximated with about a point, which means locally can be approximated with its, say, tangent line. So the line tangent to this point, to the graph of this function, can be regarded as the best approximation about the point, say if this is x0, about this point, which means just restricted to some small neighborhood of this point. You can say that this function is almost the same as this line. So I start with x0, say, and I go forward. Let me exaggerate and draw some large delta x. So if I start here at x0, then here I am at x0 plus delta x, and this is delta x. And the value of the function is this, but the value of the approximate value is the other one. So I'm going to use a different color for the approximate value in this tangent line. So the approximate value is the real value. Now I continue like this. So at this point again, remember this differential equation has its solution without the initial condition is like a family of curves. So there's another solution that goes through this point, this end point. So in a sense, I'm using that one to find another tangent line and go forward again another delta x. So x0 plus 2 delta x, and I will find this point. Then I continue like this, again using another solution which passes through this point, in fact, and then I just continue like this. And in the end, it's true that after some time, I'm just getting huge error. Now I can reduce this error, as you can see, by reducing this delta x. So if delta x is smaller, then it definitely gets closer to this. Well, I'm not saying all the time it happens. I'm talking about like nice functions, say. So if I pick small delta x, then for small delta x means that you need some kind of a calculator or a computer, or maybe a small computer program to do that for you. Anyway, so that is basically what we do here. We just go forward, delta x, delta x, delta x, and we find this point on these tangent lines. And these tangent lines are, in fact, tangent lines to other. You see, at every point there is another solution, say. Another solution, and so on. So let me give you an example on how to do this. Well, I can go with that. So let me erase this thing, and so y equals 2x plus y. Divided by x is 2x plus y. Let's assume that y at 1 is, say, 5, and find this is given, and find y at, let's not go 10, let's do 3, because it's just too much. And but yeah, if you can, so even 3 is too much because I'm going to take delta x to be 0.5, and that gives me 6 steps. There are 5 steps. So let's reduce it to, alright, so let's try to just go forward. So let delta x be 0.5. So this means that doing this. So I start at 0.15, so this is 1 and this is 5. And one solution to this passes through this point. I don't know what it looks like, but let's assume that this is what it is. Then I go forward, so this is 1 and 1/2, 2, 2 and 1/2, and 3. So delta x for me is 0.5, so I jump from 1 to 1.5, then 2, then 2.5, at the end it's 3. And I start with this and then continue the way that I described and find the value using those tangent lines. Okay, so now I draw a table, and I want to stick with this table. I have found this table is helpful, let's say. You can just write it down in several steps, but I think the table is much better. So what table? First thing we do, we have to write that as delta y over delta x equals 2x plus y, and that gives me delta y is 2x plus y delta x. Good. So that is the formula, and the table looks like this. So I have delta x here, then I have delta y, and and here I have, let's see, y. But it's x and y. It is x, delta x, and this is y, and this is delta y. Now delta y is given over there, that is 2x plus y and delta x. Now delta x was 0.5 and I start with 1 and 5, so that's my starting point. Then next is 1.5, I should find this, then it is 2, then it is 2.5, and then it is 3. So this is my goal, to find an approximate value for y at 0.3. or the value of the function at 0.3. So these are the x and y's at every step. So I start with x, y, 1 and 5, and delta x equals to 0.5. Okay, so well, I need some space here because I'm just more space. Okay, for this 1 and 5, delta y will be 2 times 1 plus 5 times 0.5. So that will be 7 times 0.5, which is 3.5, right? 7, that's 7 times 0.5, 3.5. So the next y will be 5 plus 3.5, which is 8.5. Okay, so now the second step will I will use these two. So it is 2 times 1.5 plus 8.5 times 0.5. And that equals, that is 3 plus 8, 11.5. Well, let me use a calculator here and to find it for you. So it is, what is it? 2, that is 3, 3 plus 8.5 times 0.5, 575. So here I have what's the 8.5 plus 5.75, and that is plus 5 times 7. 1425. Now I use these two, so I have 2 times 2 plus 14.25 times 0.5, and that equals, don't worry, we just have 2 more steps. So that is 4 plus 4, that's 18.25 times 0.5, 18. 9.125. 9.125. So this one will be 14.25 plus 9.125, and that equals, so let me write this below here. Then put some lines, so separating them. And this was, so this is this thing. So that is 1425. Let's add 1425. 23,375. So then I have 2 times 2.5 plus 23.375 times 0.5. That is 5, in fact, 5 plus, so I have 5 plus 0.5. 14,375. Okay, well, I'm done because there's no need to go any further. So I have 23.375 plus 14.375, and that equals so that's 14.7, 23.375. 37.75. So let me double check. So that is 2 plus 5, that's 7, that's 3.5 is correct. That is 8.5, 2 times 1.5. That is 3, 11.5 times 0.5. No, I think that's correct. So then adding this, that is 5. Correct. Then that's for 18, which was correct. So let me look at this one. I have 23.375. Then this will be 5. That's 28. No, I think this is okay. So that is Euler's method, finding an approximate value for say the solution in the function. So let's see what we can do if we solve it. So let's solve this thing. This is dy dx minus 2x equals minus 2y, sorry, minus y, sorry, minus y equals 2x. So that qt or qx, whatever that is, so I need I of x, which is mu of x, I of x is e to power integral minus 1, which is here, dx. So I have e to power minus x. So y will be, y as a function of x will be 1 over e to power minus x times integral this thing 2x e to the power minus x dx plus a constant. So let me e to the power minus x dx that times x, that is you have to use integration by what's that? You have to use integration by parts. So let me not waste your time and just do it immediately here. Okay, what do I have? I have that's x to the power minus x. So that's e to the power minus x times minus 1 minus x. So I have 1 e to the power minus x, and that is e to the power minus x times minus 1 minus x plus c. That's the integral. So so if I bring this in, that will be constant times this, that is c e to the power plus x in fact, right, and minus 1 minus x. And I have to use y at 1 is 5. Now y at 1 is 5. Now let's say y at 1 is 5 gives me 2. Well, so that is 5 equals c e to the power 1 minus 1 minus 1, right? Okay, so c will be 7 divided by e, right? 7 divided by e. So where can I write the solution? So let's erase this thing here and write the solution here. So if I write 7 over e, this will be y as a function of x will be 7 e to the power x minus 1 minus 1 minus x. Now I want y at 3, so this should be 7 e to the power 2 minus 1 minus 3. So let's see what this thing is. That's like exact values, so that's 7 times e to the power 2 minus 4. We'll do 7, 7, 2, 3, 4. So that's for this 7.723. Let's hope I didn't make any mistake. So let me plot this thing in this region. Let me double check my calculations so I make sure there is nothing. And I assume that y at 1 is 5, so 5 is this thing, e to the power 1, where is it? E to the power 1 minus 1 minus 1, that is minus 2, that is 7 on the other side. Okay, so I think it's correct. So let me plot this thing and minus 1 minus x. Okay, So let me have some space here. So let me erase this and draw the picture here for you, the graph, and show you what is happening. Okay, so this is in fact what it looks like, the graph of this function here. This is the graph of this function. Graph of this function, it starts at 1 and 5. Okay, so this can be 1 over, that's okay. So let's assume that this is 1, 5, and it goes up to point about 47 something. So if this is 0.50 and this is 1, 2, that's just too small. Let's the two. So they have different, say, so this is 1, 2, 3, and this is 5, say. So they have different scales, and this just goes up to a point here, say, like this. Okay. So what have I done here? Now this is what I have done. So I go 0.5, 0.5. So at this point I have this. Then this is the value that I have found. At 1.5, I found this 8.5. So this point is 1.5, comma 8.5, right? Then at 2, I continue like this. So at 2, I have this, and at 2, I have 2, comma 14.25, and this continues up to 0.3. So 2.5, and what am I doing? Oh yeah, that's 2.5. So then this goes here, then this goes here. So at 3, I am here. So the real value at 3, that is the calculated value using was solving differential equation 7235. So this is say, I'm not saying exact value, there's no exact value, but that is closer to exact value. But this is calculated value using Euler, and then we found 3775. Okay, so this is my error. I have this much error, which is say about 10, right? So 47.7235 minus 37.75 is almost 10. It's not exactly 10, but it's almost 10. If I just say this is 75, then I have 10. So error is almost 10. And you can see if I had chosen smaller steps, then I would have a much better approximation. I would have a much better approximate value. So if I go say 0.25 or 0.1, just take 0.1. Yeah, 0.1 it gives me lots of points here, but it also gives me a much better approximation. Now I encourage you, those of you who have knowledge, I mean, you can say write programs in any language to write a simple program and do this for different delta x's and see how close you get to that 47.7234. Okay. So I guess that's it, and Next time I will start some new subject. Okay.